There's a famous phrase that goes, everything is relative. This means that anything is quantifiable in terms of a perspective. The same goes with velocity. This is what we call a relative velocity. But what exactly is relative velocity? Before we look into that, we need to know what a frame of reference is. Imagine you're sitting on a moving train and your friend is sitting beside you. You would say they have zero speed or zero velocity because they're not moving. Pretty simple. Now, imagine you're watching the train from outside and you see your friend is sitting on a train. Although they're not moving themselves, because they're on a moving train, you see them zip across your view. These are different frames of reference. In the first frame, your friend is not moving. In the second, they're zipping before your eyes. When referring to a frame of reference, it often means that the observer is in that frame. If the frame of reference is in the train, then the observer would be in the train as well. Relative velocity is any velocity that is made with respect to the observer, or the frame of reference. The relative velocity of your friend with respect to the train is zero, but with respect to an observer outside the train or on the ground is as fast as the train. It's the same reason why when you look out the window in a moving car, it seems like everything is moving backwards. But how can we calculate relative velocity? Let's take the same train example. Remember, any vector quantity, such as velocity, comes with a direction. Let's say inside the train, a person is walking at 1 meters per second to the right. Now, you're an observer outside the train. The person walking still has the same velocity, but the train is also moving at 20 meters per second to the right. What would be the velocity of the person relative to your frame of reference, or the ground? To calculate this, you would do simple vector addition. Because both objects are moving in the same direction, if you treat the right direction as positive, the velocity of the person relative to the ground would be the velocity of the train to the ground plus the velocity of the person to the train. If the person was walking 1 meters per second to the left instead, you would do the same equation, except you would subtract their velocity from the velocity of the train to the ground. So the following equation would be the velocity of the train to the ground minus the velocity of the person to the train would equal the velocity of the person to the ground. Now notice the subscripts that come along with each velocity. These represent the frame of reference. However, velocities won't always be along the same axis. Oftentimes we have relative velocities in two dimensions, the horizontal direction and the positive direction, or the x-axis and the y-axis. Let's say there is a boat traveling across a river in the north direction. However, the current of the river runs west. Thus, the river forces the boat to not only travel across the river north, but also west along with the current. With this knowledge, we can create a diagram. Looking at this diagram, we see the river current, the velocity of the boat going across the river north, the velocity of the boat created by the river current which flows west, and the resultant velocity of the boat. Here we can see multiple relative velocities. If we look at the resultant velocity, that is the velocity relative to or with respect to the shore. If an observer was on the shore, that would be the motion that they see the boat traveling in. Now, if we look at the velocity of the boat going across the river, that would be the velocity relative to the water. If someone was in the river, flowing with the same current as the boat, they would only see the boat coming towards them. It all depends on how you look at it. Everything is relative. So the next time you're sitting in the back seat of a car, you'll know why the trees are moving backwards.